It's Paul again with some applications of eigenvectors and eigenvalues for you. You want to have a look at subtopic 1.8 of the executive summary before going through this script. We want to use rough, so we load the practical math library. And we're going to start out with a very important special case, important especially in physics, where the matrix A is symmetric. If the matrix is symmetric, there are two attractive properties. Both of these are very easy to prove in the 2 by 2 case. First one, all the eigenvalues are real. This is arguably one of the most important theorems of linear algebra, and it's a pain to prove in general. It's done in Chapter 3 of Hubbard, but the proof uses lots and lots of multivariable real analysis, which we have not got to yet. Second property, if you have eigenvectors that correspond to distinct eigenvalues, they're guaranteed to be orthogonal. And that we won't have a hard time proving in general. So here is any old symmetric matrix. I just made it up. It is symmetric. It's identical to its transpose. And we'll carry out our now very standard procedure, starting with the first standard basis vector is W, multiplying it by 1, 2, and 3, and 4 powers of A to make a matrix T. Row reducing that matrix and keeping just the last column, because as you have by now figured out, it's the last column that contains the coefficients in the polynomial P of T. And so here is P of T written as a function in R. And since this is a 4th degree polynomial, the only way of finding its roots is to plot it and see where the graph crosses the horizontal line at 0. Notice there are 1, 2, 3, 4 crossings. I knew that that was going to happen when I started with a symmetric matrix, because a symmetric matrix is guaranteed to have real roots. I was, in a sense, a little bit lucky because I suppose I could have ended up with a double root. But most of the time, you will get the maximum number of eigenvalues. What are they? Well, they're not integers. You're not going to read them off that graph. Fortunately, R has a built-in function named uniroot. And if I say I want to find the solution to P of x equals 0, where x lies in the interval from 5 to 7, it's clear from the graph that the root is somewhere in between 5 and 7. And I ask for the $ root result of uniroot. That's my first eigenvalue. The same thing works for the second one, which lies in between 0 and 3. For the third one, which is somewhere between -5 and -1, and for the fourth one, which is somewhere between -8 and -4. For consistency with the built-in function in R, I have looked for these eigenvalues in order of decreasing value. In fact, there is a function that will do this. If I call eigen on the matrix A and ask for the values, I get the same 4 numbers that I just computed. Now we want an eigenvector for each eigenvalue. The convention in the case of a symmetric matrix is to make each of these be a unit vector, so we will do that. We need a 4 by 4 identity matrix, and to get the eigenvector for the first eigenvalue, I subtract off from A lambda 2, lambda 3, and lambda 4 times I, leaving off lambda 1, and having constructed that vector v, I divide it by its own length to get a unit vector. So there is a unit eigenvector v1. I can check it. I apply a to it. I multiply it by lambda 1. I get exactly the same result in both cases. Now that we know this works, let's do the same thing to get the eigenvector for eigenvalue 2, for eigenvalue 3, and for eigenvalue 4. And as we have always done, let's bind the 4 eigenvectors together into a matrix which we'll call P. Let's calculate its inverse, and let's make a diagonal matrix out of our 4 eigenvalues. Having done that, we've succeeded in expressing A as a product of P times D times P inverse. We have diagonalized it. And not only that, we have arranged things so that the columns are orthonormal vectors. In other words, the matrix P is an isometry. The check on that is that its transpose is its inverse. Its transpose times itself is the identity matrix. R will do this in one fell swoop for us also. I call the eigenfunction and ask for the vectors. Compare that with P, and to several decimal places they come out exactly the same. Once you have the technology of eigenvectors and eigenvalues thoroughly under control, you can start using eigen for your own work. But first, be sure you know what's going on. And notice something important. If you want to prove that this will always happen with a symmetric matrix, you need very substantial mathematical skills. Computation skills will not buy you anything. But if you want actually to compute the eigenvectors and eigenvalues, you don't need skill at proof, you need skill with computing. So the two go together to make you a well-rounded mathematician. Next, let's go back and look at a Markov process. You may recall way back in Script 1.1D, we were analyzing a game of volleyball, and it started out with the probability 1 for team 1 to be serving, and then we had a little transition matrix, F, and let me remind you what that means. The first column means that when team 1 is serving, there's a probability of 0.8 that it will win the point and retain the serve, a probability 0.2 that it will lose the point and give up the serve to team 2. Column 2 gives you the same amount of information when team 2 is on serving. Now let's do something we couldn't do way back when. Let's find the eigenvalues. Usual way. Multiply W by F and F squared. Row reduce the matrix, extract the last column that has the coefficients in the polynomial P of t, make a function in R from the polynomial P, plot it and look at the results, and you see that the eigenvalues are 1 and 0.5. You could also have figured that out, of course, by using the quadratic formula. We want a 2 by 2 identity matrix, and now we're going to construct our eigenvectors. To get the eigenvector for eigenvalue 1, we use the opposite eigenvalue, 0.5. So there's our V1. Since it came out with the two components totaling 0.5, I decided to multiply it by 2. In this case, it's not a bad idea to have this eigenvector in particular be one whose components sum to 1, because then it has a nice probabilistic interpolation. Let's get the eigenvector for eigenvalue 2 by taking f minus 1 times I. And now let's plot what we've got. So there's our plot, and remember we had this red line that indicated the possible values of the probability vectors. The components cannot exceed 1, and they have to sum to 1. Now let's plot our eigenvectors on this same diagram. First plot eigenvector 1, and you say, oh yes, we've seen that before. That was our guess about what the probabilities would settle down to if the game went on and on and on. And here is the second eigenvector, and you say, that's interesting. That lies parallel to that red diagonal line, and we've already observed that too. As each point is played, the vector moves so that its head travels along that red diagonal line. Now let's plot the starting situation. The starting situation is not the same as the eigenvector for eigenvalue 1, but it differs by what looks to me like -2 times the second eigenvector. The second eigenvector has an eigenvalue of 0.5, and so every time we play a point, multiply by f, it gets multiplied by 0.5. And now that's quite clear on the diagram. The discrepancy between the original blue vector and the final red vector has been cut in half. We play another point, the same thing happens again. So we now understand completely what is going on. Each time a point is played, the component along the direction of eigenvector v2 gets multiplied by the eigenvalue 0.5. If you were to analyze a similar situation and find that the second eigenvalue was 0.3, you'd know you multiplied by 0.3 every time. And if the second eigenvalue turns out to be negative, then the blue vector will flip-flap back and forth across the direction of the red vector. Third topic. What about a reflection matrix? Well, here's an honest-to-goodness reflection matrix. It's an isometry matrix, but it has a very special property, namely it's symmetrical. I can check that it's symmetric by looking at its transpose. I can check that it's an isometry by multiplying the transpose by the matrix F. And to confirm that it's a reflection and not a rotation, all I have to do is take the determinant, which is equal to -1. So let's go after the eigenvalues. We need a three-dimensional identity matrix this time. And I only multiply by f squared. Why? Because I know what's going to happen. I know in this case that I'm not going to be able to get more than 2 eigenvectors out of a single starting vector w. So there's the matrix T. And the effect of row reducing it is to turn it into a squared minus I, which is a minus I times a plus I equals 0. So that tells me that the eigenvalues are -1 and +1. That's pretty reasonable, isn't it? When you reflect, there are some vectors that get reflected and multiplied by -1. There are others in the plane of the reflection that stay unchanged and are multiplied by eigenvalue +1. If I use eigenvalue +1 in forming f minus 1 times I will get the eigenvector for eigenvalue -1. There it is. I'll call it v1. And when I apply f to it, its sign changes. This is a vector perpendicular to the plane. So eigenvalue and eigenvector analysis has revealed to us what the plane of reflection is for this particular matrix. If I use the other eigenvalue, I have to multiply w by f plus I. That gives me an eigenvector for eigenvalue +1. That's a vector in the plane of reflection. 2 eigenvectors, that's all I was going to get from that starting point. I have to use a different w in order to get the third eigenvector. I tried using the second standard basis vector, and I got back the same 2 eigenvectors I already knew about, so I moved on to the third standard basis vector. I've changed w. Everything else is exactly the same. The eigenvalues are the same. The eigenvector for eigenvalue -1 is not new. It's the same as the one we've seen before, up to a totally irrelevant overall minus sign. But the one I get by using the eigenvalue -1, that is by multiplying by f plus I, is a vector v3 that we haven't seen before. That's another independent eigenvector for the eigenvalue +1, and now we are done. We make our matrix P by binding together our three eigenvectors. Since the first one is for eigenvalue -1, the other two for +1, the diagonal matrix that we want will have a -1 and two +1s in it. And I could, if I wanted, recalculate F as P d P inverse. One point to notice about this. I calculated the dot product of V2 and V3. That turned out not to be 0, which means that I didn't find two orthogonal eigenvectors for eigenvalue 1. I could if I wanted to. It just doesn't automatically come out that way. Our final topic is, in fact, the very first example in the Hubbard section on eigenvectors and eigenvalues. It's annoying because if you solve it with pencil and paper, you get a lot of square roots of 5 and end up with some messy arithmetic. On a computer, messy arithmetic doesn't bother us. Because numeric vectors start at position 1, I am differing very slightly from the textbook, which starts with index 0. So I'm going to start off the so-called Fibonacci series by saying I'm going to use 1 as the first Fibonacci number, 2 as the second Fibonacci number. It would be reasonable to say that a sub 0 was equal to 1 also, and 1 plus 1 equals 2, but R would not be happy with that. Now the rule for the Fibonacci numbers is that each of them is the sum of its predecessors. So if I add a sub 1 to a sub 2, I get A, and you can see this vector growing. But now I'm going to grow it by using matrices. Have a look at that matrix A and think about what it will do if you feed it the vector whose two components are A2 and A3. Well, when you multiply the top row by A3, you're going to get A3. So A3 will be the first component of the output vector. In the second row, you're going to get A2 plus A3, and that is equal to A4. So sure enough, this matrix multiplication gives us A3, which we already knew, and A4, which we didn't, and now we've extended our sequence to 1, 2, 3, 5. If I'm willing to use the square of A, I can do two steps at once and get the next two Fibonacci numbers. But the interesting thing is, let's get Fibonacci numbers way along in the sequence. Let's, for example, try to figure out the 20th Fibonacci number. In order to do that, I have to use eigenvectors. So I'll start with the first standard basis vector, make the matrix T in the usual way, and get the polynomial P of T is T squared minus T minus 1, which has been known since the days of Euclid. You can solve this by the quadratic formula. That's done in the textbook. Or you can plot it and see where it intersects the axis. If I ask for the eigenvalue between 1 and 2, I will get an eigenvalue that happens to equal 1 plus the square root of 5 over 2. And if I ask for the negative value, I will get the second eigenvalue, which is actually equal to 1 minus the square root of 5 over 2. In the usual way, I find the corresponding eigenvectors. In the usual way, I construct this matrix P, the change of basis matrix, with P made out of the eigenvectors, P, I, and V being its inverse, and D being the diagonal matrix whose two entries are the eigenvalues lambda 1 and lambda 2. If you look at these matrices, you see that the entries are far from being all integers. But all the Fibonacci numbers are integers. It's fascinating to see how that works out. In some ways, it's even more fascinating when you write things out in terms of the square root of 5. All I'm going to do is calculate PD, P inverse, and discover that I get back the matrix A. Okay. Now, as usual, it's easy to raise d to the 20th power, and in fact, it's even easier than I've said before. I warned you never to take a matrix up arrow some integer. I said that wouldn't give you what you want. But this, it turns out, is the one and only exception. When you're raising a diagonal matrix to a power, what you want to do is to raise every single entry to that power. The zeros just stay zeros when you do that. So there's the 20th power of d, and here is the 20th power of a. The 20th power of a is just what we need to turn the 5th and 6th Fibonacci numbers into the 25th and 25th, 6th. So we've now left a large gap, but we've calculated 2 Fibonacci numbers way along in the series, and we have concluded our discussion of applications of eigenvectors and eigenvalues.